This video here is on exponential functions. We say a function is exponential if it grows exponentially. What do we mean by that? So if you look at the curve in green, the function is rapidly growing toward a larger y value, or in other words, infinity. So that is exponential growth. The function in red, on the other hand, is exponential decay. The reason being, it is rapidly going towards zero. In contrast, if you took a linear function, have something like that. That is growing in a linear manner. So that is linear growth. And it's sort of a steady. But exponential in the sense things are changing rapidly. If you look at the graph, we can see the domain is from negative infinity to positive infinity. The y values start at 0 all the way up to infinity. However, we can only approach the function simply doesn't become 0 in limit as x increases significantly, or if it becomes large significantly, then the exponential function will become 0. If you look at the graph here, the point that is passing through is 0, and the general form of an exponential function is y equals b raised x, and b is what we call the base. So in this example, the base is 2. There, the base is 1/2. In general, the base is b. If the base b is greater than 1, the function is growing exponentially. If the function, or if the base is between 0 and 1, the function is decaying exponentially. So the value of b is going to determine if the function is going to grow or decay. Decay also means decreasing. So we look at the value of b, and if the value of b is greater than 1, the function is going to grow exponentially. If not, it is going to decay. The horizontal asymptote is the line along which the function goes towards 0 or plus value. So here, both the red as well as the green curve become 0 or get closer and closer to 0 as x approaches infinity or negative infinity. So it is going to go closer towards the x-axis. So the horizontal asymptote is the x-axis. Y-intercept is y equals 1. The function, an exponential function, has an inverse, and if a function has an inverse, then we call it 1-to-1. So to graph these functions, we have to know a few basic things, which are if we add c to a function, it is vertical shift up. Subtract c, it is shift down. Negative c, we shift right. Add c, we shift left and the negative and the adding happens to the x values. And if we multiply by a negative, it's a reflection about the x-axis. And if we multiply x by negative, it would be reflection along the y-axis. So, what is the base function in these three cases? It is 3, or 3 raised x, 3 raised x, and 3 raised x. So let us start with the base function. We know it is an exponential, and all exponentials will look the same except for the y values. And since b is 3 in our case, it is going to grow. The reason being the value of b is greater than 1. So the function's going to go of that sort. So that point is 1, and the reason being when we plug in x is equal to 0, y would equal 3 raised 0, which is 1. So that is that point over there. And perhaps we'll just have 2 points. When x is equal to 1, y would be 3 raised 1. We end up getting 3. And x is equal to 2, y would be 3 raised 2. We end up getting 9. So in the first problem, we are subtracting the value of x by 1, which would imply that the function is going to shift to the right by 1 unit. So we know the base graph is 1 when x is 1, y is 3, x is 2, y is 9. And it's going to go like that because it's exponential growth. And since we are going to subtract 1 from x, the curve is going to shift to the right by 1 unit. So I'm going to draw this in black. So shift there by 1 unit, 1 unit shift, and 1 unit shift. And we'd have something like that. So in the second case, we have the base function and we're subtracting 1. So the base function is going to go through 1 and 3 and 9. We're going to subtract in the sense the y value is going to reduce by 1. So we will have 0 here. 2, and when it's 2, it's going to be 8. So perhaps I shouldn't do that. So let's make this larger. So that is 1, 3, and when x is 2, y is 9, and it's going to grow and go up that way. The second one, which is our actual function, we are shifting down by 1 because of negative 1 there. So it would be here, there, and at A. So it's going to go up that sort. The red line is actually going to go along y equals -1. The reason being, of course, we are subtracting it by 1 here. The asymptote is along the whoa, what's happening? The black line here is going along the x-axis, so the asymptote is the x-axis, and the red one, it's shifting down by 1, so it would become y equals -1. The reason being x-axis is y equals 0, and if we subtract 1 from y equals 0, it is going to bring it down to y equals -1. So the next case is y equals, or f of x is equal to -3 raised x, and the base function here is that. And we know that if we multiply the base function by a negative, the curve is going to flip about the x-axis. So that is 1, 3, and 9. So that is the original function, y equals 3 raised x. And the base function would simply flip because we're multiplying it by a negative. So it has to go through -1, -3, and -9. Graphs are too small. And on the other side, it would simply move along the x-axis, but it has to go through those points, and it would be the reflected version of the original function, y is equal to 3 raised x. So in the previous problem, the base was 3. We have a specific base called the natural base, which is denoted by the letter e. So the function y equals e raised x, or f of x is equal to e raised x, is the natural base exponential function. And what is the value of e? The value of e is 2.71828. And you can see that the graph of e raised x, it looks like any other exponential function. For example, we could look at y equals 3 raised x over here, and y equals 2 raised x over there. So every exponential function, pretty much they look the same. The only difference here when we use e is that we call it the natural base. Different calculators have different options when it comes to exponential functions. So depending on the calculator that you intend to use, you can easily find a button that says E in the calculator, and all we have to do is plug in the value for x and we will get the value of an exponential. So here we are trying to evaluate e raised 3.4, and that would be 29.9641. So if you can't do it that way, you could also do 2.71828 raised 3.4. It should give you the exact same answer, or something very close. Plug it in the calculator again. And lastly, this is an exponential function, but we have 5 raised to the power of root 3, which is 5 raised 1.732. You can use, typically in a calculator, this is x raised y. So most calculators would have the button as x raised y. For instance, that right there has x raised something. So in our case, x would be 5, and that square up there would be square root of 3. So if I plug this in the calculator, I get 16.2425. So we all have credit cards, and they have variable rates, and typically interest when it is applied in credit cards, the interest rate is compound interest. And the simplest formula for compound interest is P times 1 plus R divided by N raised to the power N times T. Where P is the initial amount of the loan and N is the number of times we apply the rate, because we are compounding the interest, and T is the time for which you have this particular loan or investment, or anything that involves compound interest. Here, the key thing to notice is that N is the number of times we apply compounding. But if we have to apply interest in a continuous fashion, in other words, we don't have a fixed number of times when we apply the interest, rather than continuously throughout the year we choose to apply the interest, then the formula reduces to P times E raised RT. But just think of the deodorant part. So this case is when we apply the interest continuously. And E is our usual natural base. And that approximate value is 2.71828. So here is an example where you have $6,000 to invest. Which investment yields the greater return over 4 years? 8.25% compounded quarterly, 8.3% compounded semi-annually, and 8.2% compounded continuously. So the principal amount here is 6,000, and the rate is 8.25% for the first case. It is quarterly, so we are going to apply the interest 4 times per year. And the time is 4 years. So using the formula, we simply plug in 4,000 times 1 plus. Do not forget to convert the percent to a number. Oh, that's a bad choice there. So it would become 0.825 divided by 4 times per year, so n is 4, and 4 times 4, we get 16. So you can use a calculator to evaluate this. And the amount is 5,545.226. So the first case, the interest accrued would be that amount minus the principal, so 5,545.226 minus 4,000, you end up getting 1,545.226. The second case, the rate is 8.3% compounded semi-annually, so the principal doesn't change, it's 4,000. The term doesn't change, it's 4. But number of times is 2 because we apply the rate 2 times per year, semi-annual. And the rate here is 8.3%, so that would be 0.083. So we use the formula. A is equal to the principal times 1 plus r over n raised nt. So 4,000, 1 plus 0.083 divided by 2 raised 2 times 4. So we would end up getting that, and you can use a calculator as always, and we end up getting 5,537.761. So the interest accrued would be this final amount minus the principal, which should be $1,537.76. The last case is 8.2% compounded continuously, so this would imply the formula is A equals P times E raised RT. P is 4,000. The rate is 8.2% now. So the third case is 8.2%. The time is still 4 years. Since we are compounding continuously, we have the formula per. So 4,000 times E raised 0.082, converting percent to a decimal, times 4, which should be 4,000 E raised and use a calculator. and we get the amount as 5,552.76. I'm sorry, 5,552. So the interest accrued in this case is the amount, the final amount at the end of 4 years minus $4,000. We get 1552.76. So the three cases, 8.25%, 8.3%, 8.2%. The term is fixed, the principal is fixed. N initially was 4 times, that would mean quarterly. 2 times, semi-annually. And the last one is continuously. And the accrued interest case 1 was 1545.23. Case 2, 1537.76. Last case, 1552.76. So obviously, continuous compounding is the way to go. Even though the rate is small compared to the other two cases, we get a better yield at the end here because of the fact we are compounding continuously. Unfortunately, most investments do not compound continuously.